Uh, my name is Jian Fen. I'm from Huawei. It's our pleasure to share our experience in Spark streaming with you. At today's talk, we're going to have two parts. First, I'll present you StreamDM. It's a string data mining library in Spark streaming. Then Chen will talk some business scenario in Huawei with Spark streaming. So there are many open source machine learning projects. I'm only mentioning a few of it. So the first one is Apache Mahat. Apache Mahat is a distributed machine learning library for Hadoop. Then in 2014, Mahat released Mahat Samsara. It now can run tasks in Spark and H2O. Then in the last version, they can support Flink now, and they also provide R-like DSL Scala API. So it'll be quite convenient for users of R. Then another project, the ORYX, is distributed by Cloudera. The first version is support the Hadoop. It's a real-time, large-scale machine learning project. Then last year, they released version 2, and now can run in Spark streaming. Another project I want to talk about is Samoa. Samoa is distributed by Yahoo Research Lab. It's a distributed version of the MOA. Currently, it can run in Storm, Senza, and Flink. It's a string data mining online project. And I also want to mention one of the main contributors of Samoa, Albert Buffett. He's also working with us in StreamDM. So what is string data mining? When we talk about data strings, we are receive data continuously in very fast. So we are not able to store all the data for offline processing. We have to process the data very efficiently. And the data may be evolving. The data distribution may changing from time to time. So we have to make our model, our learner, to adapt to that situations. And in many cases, the exact solution will be very expensive. So we're going to use some approximation algorithms. That means that the algorithm should have small error rate with high probability. Then what is StreamDM? First, let's take a look about Spark streaming. In Spark streaming, the data is not processed by one. It was processed by a mini batch or micro batch. Spark streaming uses a data structure called dstring, and the dstring is a sequence of the RDD. And in StreamDM, for each partition of the RDD, we will use a model to chain it. Then for each RDD, we're going to merge these models and update the model. So all the algorithm in StreamDM is incremental. Then why you're going to use StreamDM? StreamDM is very easy to use. First, you only need to download it from the GitHub to build it. And here's the example how to run the tasks on command line. In these cases, you're going to use SGD learner with its parameters and use the file reader to simulate a case of this string. You read it from the file, and the duration of the RDD is 60 seconds, and each RDD had 100 examples, and you output the result to the logs and the file and the result files. And the StreamDM is also very easy to implement it. There are 5 components of StreamDM. So first, the string reader. String reader is kind of wrapper. It can read and pass data from the files or sockets and create the string. And the string writer will output the result of the string to console or to files. For the algorithm programmer, mostly only concerned about implement the learner and the model. The model will provide the trim function for input strings, and the model will contain the data structures and also the delta data structure, and also a set sort method called by learner. The evaluation is help to evaluate the predictions. So in these cases, when we're gonna go a little details about how to make it work. So usually when we do batch processing, we use a bunch of data for training, then another set of data for test. But in our cases, let's suppose we're gonna receive a data with labels. First, we're gonna predict it with the current model. Then we use this data to update the model, get a new model. So all the algorithm in 3DM is incremental. And the last I want to mention that 3DM didn't depend on any third-party libraries. For example, the linear algorithm package Breeze. We can support sparse and dense data with the basic functions, and it works well. In our last release in last year, we currently have SGD, perceptron, naive Bayesian, class string, Hovden decision tree, bagging, string cam, and plus. And then in the next release, we will support Spark 2.0, and we will have random forest, frequent item miners. You may be said, oh, there's so few. Yeah, that's why I'm here. I want more people to know it, to use it. If you do similar work in the Spark string data mining, or you do research on it using Spark streaming, you can use it and you can pull request. So in the first part, I'm gonna share something else with you. When data science to do data analysis, they maybe use R or Python to handle the sample data. But when they have to deal with big data, what are they gonna do? They have lots of platforms like Google Cloud Dataflow, Spark, Flink, and Storm. There are lots of machine learning libraries, MLlib, Mahot, or something for string mining like Huawei, StringDM, and Samoa. What are they gonna choose? And before, they maybe have to pick one. Like us, we choose Spark streaming. But now they maybe don't to do that. Now there's an incubator in a patch called Beam. It tries to provide the interface and SDK for different platforms. So the user, they're going to write the application, and it can run in Dataflow, in Spark, and Flink, and Storm. Maybe we can do something the same for machine learning part. In my opinion, there are two solutions. First, you can write all the algorithms in BML, then it can run on different platforms. In that case, there's a lot of work to do. You have to implement all the methods, all the machine learning algorithms. Another way, you can make a BML as an API. It's gonna use, so it's gonna call different machine learning package for different platform. Like you may call MLlib in Spark, you may call Samoa from Flink, something like that. That depends on all of you. So this is the first part. I'm gonna let it my turn to present the second part.
Okay, thanks for the introduction. And I'm He from Lost Ark Lab, Huawei Research. So now I will try to introduce several of our business scenarios to you, and I will try to start with some specific challenges in telecom big data analytics. First I'll try to skip the 3 V's. I believe you all know them very well, and I just directly get into the other 3 of them. 95% of our network generated data are data streams, which are continuously and infinitely. And most of them are without predefined feature vectors. So, traditional machine learning and data mining algorithm cannot be directly applied to such data set directly. And the second part is the different kind of data are extremely imbalanced. And the positive data sample, the level of positive data sample are difficult to get. Finally, concept drift always exists in most of the applications because of the dynamic of network configuration, network environment, and user's behavior. So batch analysis and single model are inefficient and inaccuracy in these scenarios. So I'll start from the first case, alarm analysis. This is from the network device point of view. We can get data directly from different network devices. And first of all, I'll show you some background, the standard workflow for how to using alarm by locate the network problem and fix the problem. First of all the network devices, when they come from some bad scenarios or bad things like link failure or traffic congestion, they may emit alarms to the fault management system. And after that, the engineers and the experts in the network or development team will try to do some root cause analysis based on these alarms and their previous experience and domain knowledges. And after that, they may describe the potential solutions and details into trouble tickets and assign the task to the field engineering to fix the problem. But things will become quite different in the near future cloud-based services because we may face 40 to 100 minutes of alarms per day. And the patterns inside this alarm events may be changed rapidly and even with some unnoticed or unmodeled phenomena. What are we going to do? Traditionally, expert-based solution may become a bottleneck. So inside the company, we design our solution, what we call automatic alarm behavior discovery engine. First of all, we try to capture as more as possible of different kind of data set into all level of network, and we inject them into our AABD engine. Inside the engine, actually the engine is based on Spark platform. Inside the engine, we implement some classical frequent pattern mining and sequential pattern mining algorithms. And then we, based on this kind of specific data and domain knowledge, we optimize these algorithms and try to find out inherent correlations among these alarms and automatically generate rules for future deep analysis such as alarm correlation, root cause identification, fault penetration, and even forecasting. Currently, we finished the first task of doing alarm correlation in single domain. And at the very beginning, we implement our algorithms in Spark based on the MLlib API. And now in order to handle the data streams, we are trying to implement our streaming version of algorithms in StreamDM API, as Jennifer mentioned before. And fortunately, we contribute our offline version to the MLlib, and all the algorithms like FG growth and prefix span has already been accepted and become the standard toolkit in MLlib. And in the future, we will open source our streaming version of algorithms in StreamDM and try to contribute them into the community too. And how about the result? We have already deployed our solution in more than 13 operator sites all over the world. And we got several numbers. We can improve the efficiency of deployment from 5 man-months to 3 man-day. And we can handle millions of alarms sequences within 1 hour, and which means more than 30 times faster than state of art. So in the near future, we'll try to get into the cross-domain alarm coordination, and based on Bayesian network and other AI techniques, we may try to get some root cause inference in the near future. And the second case is how to do the fault localization for customer care. This is higher level of the network compared to the device level. The same as before, I show you how I show you standard procedure currently inside the operator. When the user feel bad experience about the services provided by the operator, they may make complaints. And the poor guys in call center, the customer service staff, maybe only can check the complaint query system and find the limited information which may be manually inputted and cannot be updated on time. So if she cannot handle the problem, she may, based on previous experience, give an ambiguous feedback to the users, which may render the customer become even more angry. And meanwhile, she may push the difficult issue back to the engineering team. And the experts and managers from engineering team and the other department of the operator will maybe get involved into solving the problem based on their domain knowledge or privacy experience, or even get details into the log file or even singularly events. And after that, they may feedback some results. And all this may be several hours or several days delays. And if something fortunate, the good part is sometimes if they feel confident about their decisions, they may hard code the rules into the system and in case for future reusage. And the problem is difficult, even difficult than alarm analysis, because we cannot predict which user will make complaints in the future. So we may analyze all customers' data, which number, maybe several order of magnitude larger than network devices. So the same as before. Only traditional expert-based solution will become a bottleneck. So what we want to do is try to provide intelligent customer care assurance solutions based on automatic feature engineering and combined with expert rules to some of our ensemble classification model to provide immediate response to the call center guys. But things will not be so simple like 4 building blocks I present here, I show here, because there are several challenges from pattern mining in these large data streams. Basically, it's an NP hard problem. We will try to search the complexity of S to the power of S, where S means the sample size, because usually some anomalous things or failures only happens infrequently. So we must mining lot of we may mining lot of patterns as noises and inject them into the models to get an inaccurate result. So there are several state-of-the-art solutions. Based on divide and conquer solutions, we can reduce the complexity based on the model-based search tree. So, but the problem is they can only handle the offline batch data. So what we're going to do is try to design a new way to handle online streaming data by online stream mining algorithms. We can, based on Hofstadter bound, we can dynamically build our model-based search tree and further reduce the complexity until we can practically deploy it into the real network. Before our deployment, we use existing open data and some of our data to do a lot of offline tests. Fortunately, we get some results as we expected. First, we can have much better efficiency in terms of time, expense, and memory usage, while we can also preserve the accuracy. And second part, we can fastly detect the concept drift and generate stable and discriminative patterns for future ensemble classification models. Finally, we cautiously design our building blocks, and it's more complicated than I showed before, including data preprocessing and sequential pattern mining, pattern matching, and model update. And we implement the online part into Spark Streaming and the offline part into Spark. Currently, we'll handle 4 to 6 terabyte data per day, and we can provide immediate feedback within 3.6 seconds and get model update within 5 hours. 5 hours because, as I mentioned before, the labels are very difficult to get, so we can only update models every 5 hours when we get new labels. Okay, so there are some more applications, practical applications inside the company. So by deploying our solution into the real systems, we earn some lessons. First, about Spark. Of course, it has a lot of advantages. The first one is it's easy to use, especially for our research team. It's easy for us to build a proof of concept solution and quickly get the result to to further improve the model, the algorithm, and the system solutions. And the second part is it has a perfect community and ecosystem. We got a lot of support from the community and a lot of new functions and algorithms. But it also has several limitations. First, it's not a real data stream processing engines. It can only provide batch or mini batch or micro batch processing, so it cannot provide a guaranteed delay or throughput. So that's why inside our company, we have our own distributed stream processing platform, what we call Stream Smart, which is implemented in C++. And we use our Stream Smart into several scenarios with critical model update requirements. First one is the Huawei smartphone app recommendation, and we'll face more than 100 million customers and more than 30 million to 100 million features. And the product team asked us to update the model in second level. So that's why we choose Stream Smart. And the second part is in IP backbone networks, we'll try to do the online anomaly detection and anti-DDoS detection. So we'll try to face 4 million to 10 million flow per second. That's why we also need a very high speed and low latency systems. And the other part is about data analytics in telecommunication networks. We feel that, first of all, as I mentioned, 95% of the data are infinite and continuous streams. So efficient sequential pattern mining framework is very important because we can find discriminative and essential patterns for further classification and supervised learning. And second part is cutting-edge technology like deep reinforcement learning will be applied in the network resource management, anomaly detection in the near future. We are all focused on that. And the third part is we think robust AI and machine learning algorithms are equally important as domain knowledge. Usually we must combine them together to get the expected output. Finally, how to evaluate, how to build a closed loop evaluation is also very important for us. That's lessons we get from several practical applications. And finally, a small end, we will have Huawei HIRP program, which will provide funding and opportunities to leading university and research institutes. And one sub-project of that is related to our StreamDM and telecommunication network data analytics. So if you feel interested, you can contact us anytime if you're interested in such a program. So that's all. Thank you so much.
Thank you, guys. Q&A? Got 7 minutes. Let's torture them. Just kidding. No questions? Oh, here we go.
You mentioned that Spark streaming has this latency concern. So can you give some example, like in your typical use case, what's the like batch interval for the NT
okay. I didn't show the benchmark testing between Spark streaming and our StreamSmart, but I can show some figures. Inside our company, we test several cases between these two distributed platforms, and usually our StreamSmart has less than 1 second delays, latencies, and Spark streaming usually have something like 10 to 20 second delays. But why we choose Spark streaming, as I mentioned, because it's easy easy for our research team to build our solution, and because we majorly focus on algorithms, and we need fast proof of concept, and later we will transfer our techniques to the product team, and they may focus on performance. So that's why we choose both of the solutions, and usually the first choice may be Spark streaming for POC, proof of concept, and later for transfer to the platform, maybe StreamSmart. Yeah.
So you're saying in production you're using different technology?
Based on scenarios and different requirements. If you want to update the model based on second level, maybe you try to choose StreamSmart. Maybe the model will not be updated so frequently, maybe you can use Spark streaming. Yeah, based on different scenarios. Thank you.
Any other questions? Oh.
Yeah. Would you be able to share with us about the size of the cluster in production?
Pardon? Excuse me?
I mean, like the architecture, the infrastructure.
Oh.
I mean, your production system. What does it look like?
Production system. I think looks like what Jennifer mentioned at the beginning. It's sorry. It's sorry. Maybe I can use some figures later. Production systems. This one. I didn't draw a general figure because different scenarios we may design different solutions, but majorly it will include several major building blocks. First is the data preprocessing, and especially for data streaming analysis. First one is the sequential encoding, and some missing data. We're trying to handle some missing data or error data, and after that we do sequential encoding. And then the feature engineering part. we have automatic feature engineering techniques as well as our expert feature rule engine. And after that, maybe the data mining and machine learning part. We integrate several algorithms inside. And the final one is specific application and label feedback for updating the model. So I think this is a general picture of the end-to-end solution. But as I mentioned, the more general we get, the hard to deploy into specific case. So we didn't draw the general picture. It's only, it's not so useful for specific product. Yeah.
But what's the size of the cluster that you
Oh, that's a good question. In fact, in telecommunication scenarios, usually we get compact size because the operator site usually have limited space. So at most we can get 1 to 3 racks, maybe limited to 30 commodity servers, yeah, 30. But with that, we can have the capability of handling more than 10 million transactions per second, and nearly 100 terabyte data per day. Yeah. That's enough for telecommunication scenario. Thank you.
Any other questions? Okay, well, thank you very much.
Okay,
Big welcome.